Dr. Brian Snyder here with us. He is an orthopedic surgeon at Boston's Children's Hospital, as well as an associate professor at Harvard Medical School. So he obviously has a lot of experience in the STEM fields, and he'll be able to share that with us tonight. So welcome, Brian Snyder.
So when Russ asked me to do this was actually a lot of fun because it was right around when I was your age, taking AP physics in 11th grade, that inspired me to end up doing what I'm doing now. And, you know, it was doing a problem set in statics and mechanics that was the physics of the human body. And to me, that was just amazing because up to that point, you know, it was sort of what's the parabolic of a rocket ship, or there were two cars going at different velocities. But then all of a sudden there was this problem set that was like, you're carrying, you know, a weight this far, how much does your deltoid muscle have to support? And it was like, for the first time, it sort of just connected that, like, the physics that I was learning, you know, these abstract concepts, could actually be applied to the human body. And that inspired me to go into bioengineering. And back when I was applying for college, there weren't a whole lot of bioengineering programs at the time. And it was an emerging field. And I also decided through bioengineering to go into orthopedics, because orthopedics is essentially the musculoskeletal system, but it's sort of the structural mechanics of the musculoskeletal system. So I titled this, you know, if you want to be a doctor, you really need to learn high school physics, because it really explains a lot. Now, granted, a lot of my talk is going to be much more orthopedic based, and orthopedics is the field where we do musculoskeletal medicine. And that's broken bones and sports injuries and back pain and things like that. But a lot of what I say could also be applied to the vascular system and fluid mechanics and cardiac and renal, which is physical chemistry. So a lot of the basic science stuff that you're learning now, you know, chemistry, physics, and calculus, and linear algebra, really do have applications beyond those sort of boring problem sets that you have to go through. So what I'm going to try to do is kind of give you like a little physics class, but show how that can be applied to the human body and explain a lot of things about how you walk, why your bones break, what happens when you get osteoarthritis, and how your bones heal. So just as a quick, how many of you are either have had or are taking high school physics now? Okay, so a lot of the concepts here are probably going to be familiar to you. And for those of you that may not have had high school physics quite yet, because you're going to have it next year, this is some of the stuff that you can look forward to. And I'll try to explain the concept. So there's no calculus here. There's nothing really sophisticated. But it's really to give you a flavor for what it is that you're learning now, but how this actually can have meaning to you in the future. So the first thing I'm going to talk about is what we call rigid body mechanics. What that means is that the bodies don't deform. They're sort of rigid. So like that chair, and how that chair would maybe move through space if I picked it up and I threw it across the room would work. And this is a review for probably a lot of you who've already had physics, but I'm just going to say force is a vector. And what that means is it has a magnitude, it has a direction, and then it has a sign. So we use the concept, if it's compression, if I'm pushing down into something, that's actually a negative. Whereas if I pull it, that's a positive. And then it has specific units, and we often use newtons, and it's kilogram per meter second squared, because that's showing, that we'll talk about Newton's law in a second, that's a mass times an acceleration. So when you're walking and your heel hits the ground at heel strike, there's a force that's being transmitted up through your legs in a direction towards your hip joint. And there's all kinds of different forces. There's contact forces. So this is the patellofemoral joint. This is your kneecap. And you can look at what is the force between the back of the kneecap with the femur. Now we can either model it as a point, but in reality, it's a whole surface. So there's actually that force is distributed over a surface, and we sometimes call that a stress or a pressure. But you can also have gravitational forces. So the reason the sun, the Earth and this planets revolve around the sun, that's gravitational force. So you can have these contact forces, or you can have body forces. A moment is when you have the twisting effect of a force. So that results from the application of a force at a certain distance from a real or potential axis of rotation. So if I'm trying to take the lug nut off my car, I put the wrench on, the center, the axis of the lug nut is my sort of point of rotation. And what happens if I'm too weak and I can't actually knock it off? I get a bigger moment arm, because the moment is the force times that distance. So I'm weak. I can only certainly generate a certain amount of force. But if I get a bigger moment arm, I can multiply that force. And that's why a 3-year-old can balance your father, like a 27-year-old on a seesaw if the father sits really, really close to the fulcrum and the child sits way back. Because it's that force times a displacement. It's that product that's important. And I'm going to show you how that has certain meaning in the human body as well. And just like force, moments are vectors. They have a magnitude and a direction. But the concept that we use is the so-called right-hand rule, where you sort of rotate around. So in this case, if I'm rotating this way into the paper, into the board, we call that positive. If we're bringing it this way in the opposite direction, that's negative. And it also has units, Newton meters, or pound inches. So the foundation of physics and the physics of the human body is really based on Newton's laws of motion. So the first law is inertia. If there's a net external force acting on a mass, is zero, the mass will remain at rest or move uniformly. So in other words, if the mass is sitting there and I don't push it, it's going to stay there. If I'm pushing it at a constant force, basically it's going to move at a uniform rate. Acceleration then is the net acceleration of the mass, and it's proportional to the applied force. So this is the so-called equation force equals mass times acceleration. For gravity, instead of A, this is the gravitation acceleration. And the third law is for every action, there's an equal and opposite reaction. So, what's an example? Woman sitting in a chair. The chair and the woman are at static equilibrium. In other words, she's staying there. She hasn't moved. The weight of her body is the reaction force equal to the chair's pushing up on an equal force that she's pushing down. But if I pull her chair out, so if this is like you're playing a prank on one of your buddies and you pull the chair out from them, they're going to fall down because her body mass is no longer balanced, and she's going to fall at this rate generated by force equals ma. Now, this is actually the problem that I had in my problem set in high school physics that actually captured my imagination and I thought was really neat. And it was saying, here's some guy holding a mass out like this. What's the force in the deltoid muscle? And what they were trying to do is use this idea of free body diagrams. And what you do is you simplify the system. Instead of having all these complicated muscles and stuff like that, you sort of get it down to the brass tacks. So what you do is you isolate the object or the part of the object from the environment. So we're going to look at just the glenohumeral joint. That's your shoulder joint. And the deltoid muscles, this deltoid muscle, guys of you that sort of work out, you try to make that big. That's what holds your shoulder out. So then what you can do is you can say, okay, well I have the mass and it's operating at some distance away. I have the direction of my deltoid and I can basically model that as a force vector. And then I have a reaction force at the shoulder joint itself, the glenohumeral joint. And in fact, you can solve this by drawing the vectors in very specific directions and forming a triangle. So that basically you can actually solve this in a geometric way. But the better way to do it, and the more convenient way to do it, is to use math. So here we have the equations of static equilibrium in 2 dimensions. So translational equilibrium, meaning, so I'm just in plane surface, the sum of the forces have to equal 0, and rotational equilibrium, the sum of the moments have to equal 0. How's that break down? So if I split the force vector into its component parts, sum of forces in the x direction, sum of the forces in the y direction have to equal 0. And then the sum of the moments all have to also equal 0. So these are sort of Newton's laws broken down into practicalities. So this is what happens if your grandmother breaks her hip. She has a broken hip. This is a common device that's used. It's called a dynamic hip screw. And you see that basically, here's the fracture. This plate is sort of holding that fracture together. And I've got a little gap here. And if the question was, how much force or what moment must this plate support so that this doesn't collapse, that that fracture goes on to heal, it's this problem. I have a force being applied at the hip, and I have a moment arm, which is this distance. Here's the trajectory of my force. Here's my D, the moment arm. So basically, this has to be strong enough to be able to balance force times D. Now what happens if it can't? This is what happens. It falls apart. The plate falls apart because the fixation was not sufficient to resist that applied moment. This is a real patient. This is really, this stuff happens. So when you're trying to figure out how you're going to fix this, you want to make sure that that doesn't happen. So how can you prevent that from happening? Well, we know that the magnitude depends on the length of this moment arm, because I can't really control the force. The force is body weight, or the force is the reaction. If I use a 90-degree blade plate, that means that basically I have a much bigger D here. Here's my joint reaction force. If I break it down into its components, this is a big D. But suppose I do a angled blade plate. So it's going to be the cosine of the angle. So the moment arm is going to be smaller, so that this plate is better able to resist any force that's being applied. And in fact, this is how you bail out that case. Is you would say, okay, this fixation was insufficient, but if I go to a higher angled plate, I can help compensate for that. Now this was supposed to be a OpenSim gate analysis. It didn't transpire when I went to the Mac. But basically, what I want to show you in the next sort of set of slides is we can break from the very concepts I just taught you here, and if we think of walking as sort of your hip as a simple hinge, your knee as a hinge, your ankle as a hinge, and these basically as moment arms, we can start understanding gait. So gait is a sequence of single limb functions during walking, and we break it down into a stance phase. So when I'm walking, I have part of my is walking where I have one or both feet on the ground, and the other is swing where the leg's swinging around. So 60% of a gait cycle is in stance, and 40% is during the swing phase of the gait cycle when one limb is sort of not touching the ground. Now, if we simplify the problem, and I want to know the main muscle that supports this leg, when I'm standing like this muscle called the gluteus medius is supporting my whole body weight, 5/6 of my body weight, because 1/6 is the leg itself. And if I want to know how much force is in that abductor, that gluteus medius, or what is the joint reaction force? I can calculate that by doing the free body diagram that I just showed you when we did the deltoid. So we certainly can do a graphics where I draw the vectors in the right orientation and their size representing the magnitude. But we can also do it just like we did before. To keep this simple, let's just say that the gluteus medius, the direction is purely vertical. There's no angle to it. So we're going to say some of the forces in the x direction are all 0. What are the sum of the forces in the y direction? Well, I have my abductor force, my gluteus medius, so that's pointing down. I have my joint reaction force, which is at the hip joint, that's pointing up. And then I have 5/6 body weight pointing down. So if we basically write this, sum of the forces in the y have to equal 0. Okay, now what are my moments? My abduction force, the gluteus medius, is acting at a distance a from the center of the hip joint. And that's going to be balanced by 5/6 body weight that's operating also from the center of rotation at the hip joint, and that's b. And then sort of the convention is that since this is coming out, that's going to be negative, and since this is going in, that's going to be positive. If we collect our terms, that means that the force of the gluteus medius is 5/6 body weight times this ratio b to a, and the joint reaction force is the same thing but 1 plus b to a. So let's put typical values from x-rays. So for a typical adult, 200-pound male, that A is 5 centimeters and B is 15 centimeters. What that means is my gluteus medius must generate 500 pounds or 2.5 times body weight. And the joint reaction force actually comes out to 3.3 times body weight. What that means then is for every pound over your ideal body weight, your body, your gluteus medius, has to actually work 2.5 times extra for every extra pound you are over your ideal body weight. But more importantly, everybody has heard of osteoarthritis, and we'll talk about that in a second. That means for every pound over, I'm actually adding another 3.3 pounds of joint reaction force that's going to make your hip joint wear out even faster. This simple, very simplistic two-dimensional, is that real? Well, it turns out that Bill Harris, who was at the Mass General and one of the pioneers of total hip replacement, actually took total hips and instrumented them and actually measured what are the contact forces during walking in real people. And in fact, you can see that during walking, you're generating about 3.3 times body weight. This simple two-dimensional, sort of very simplistic, closed form solution was able to actually tell you sort of what people are applying to the real body. So I can explain walking. But more importantly is, let's see if this works. Okay. You see how she's limping? That's called an abductor lurch. She has a weak gluteus medius muscle. So when she is in single stance, she can't support her weight. So what does she do? She drops it. So that causes her to walk with this limp. So this abductor lurch or limp is caused by a weak abductor muscle. It can't generate the adequate abductor moment. But what's a simple way to fix that? If I put a cane in the opposite hand, what am I doing? The force of the cane is contributing and augmenting the abductor moment. So from this simple two-dimensional problem, I can explain why somebody's got a limp, and why if you put a cane in the opposite hand, you'll actually make their limp go away. And that's why when the doctor, a lot of times you'll sort of say, the natural thought is, well, if I'm going to put a cane, I'm going to put it in the same side as the affected, as where my leg is hurting. That's the wrong answer. It's in the opposite hand has the most benefit. So I don't know how many of you have ever had an injury to your leg and you went to the doctor or the orthopedic surgeon and you had to use a cane or something like that. But that's why they tell you put it in the opposite hand. What this also shows is that synovial joints allow very large rotations in response to very small displacements or contractures of the muscle. So when if I'm going like this, kicking, this muscle, the hip flexor called the psoas and the rectus femoris, those muscles are acting over very, very short moment arms in the bone to have a large excursion so I can kick a football. And that's generating a lot of force. But to allow large displacements or rotations, it means that the muscle is acting at a mechanical disadvantage because the moment arms are very small. It's that seesaw problem that we had talked about back in the beginning between sort of a 3-year-old trying to balance his father. The consequence then is that you have very large joint reaction forces that predispose to degenerative changes. Which brings me to osteoarthritis. So how many of you know somebody that has osteoarthritis, has arthritis of the joint? Some of you probably have it if you're athletes or you've had an ACL tear or you've had an injury. So osteoarthritis is a chronic non-inflammatory disease that affects the articular cartilage. There's progressive breakdown, and it's most commonly because of mechanics, because you're overloading that joint. And this is sort of what it looks like. Healthy cartilage, it's nice white slot, very slippery. I don't know if you've ever looked at a chicken bone, you pull the chicken bone, it's that nice white. It's got a coefficient of friction of ice on ice. But then when it starts to wear out, it starts getting kind of spongy and not so hard and very, very soft. And that's what happens in osteoarthritis. The reason we get osteoarthritis is because we have friction in our joints. And if you all remember, or I don't know if you had it quite yet, but friction, the force of friction is related to the coefficient of friction times the normal force that's applied perpendicular to the surface. And coefficient of friction for any two materials is a unique property. So for wood and plastic, for plastic on this rug, those all have unique coefficients of friction. For a joint, cartilage with synovial fluid, which is the sort of the oil in our joints, the lubricant in our joints, that number is 0.002. It's a really small number. As a comparison, total hip replacements, the metal plastic that we use, that maybe your grandmother had, a total joint replacement, is on the order of 0.05. It's 10 times higher coefficient of friction. And what happens is, if I have a high coefficient of friction and I'm moving back and forth, I start to wear out. I'm like sanding that surface. And that's what happens in osteoarthritis. I basically am wearing out, I'm rubbing off that cartilage. What cartilage does, though, is it really has this unique capability called elastohydrodynamic lubrication. What that means is the cartilage is like a sponge. It's porous and it holds fluid. And if I squeeze it, if you squeeze a sponge, there's a little bit of water that comes out. What happens is when I squeeze this when you're walking, it squeezes a little bit of fluid and it forms a fluid film that acts as a lubricant and also helps share that load. Instead of that force being over this pinpoint, it improves the total surface area of contact. And that's how our body compensates for these large forces at joints and basically tries to negate the effect of friction. Okay, the next part it's also kind of neat out of physics is strength of materials. How's a bone break? A fracture occurs when the load being applied is more than the load capacity of the bone. So in other words, there's a certain amount of force that this bone can basically support. And if I exceed that, it's going to break. And the factors that affect fracture risk come down to the material. What's the bone material itself? What's its intrinsic strength? How then is that material arranged in space to form a structure? So our bones are unique in that they have this tubular structure. At the ends where our joints are, we have sort of this spongy bone that can absorb load, and it's covered at the joint top and bottom with that cartilage so that we have this sort of hinge joint that has very low friction. But then it also depends on what are the loads being applied to the bone. And when the load is bigger than the load capacity, that's when fracture is going to happen. Stress is the force divided by the area. It's the internal force intensity that resists an applied load. And we can have normal forces, which are sort of perpendicular to the surface, and shear forces, which are parallel to the cross section. An example of shear is how scissors works. When I'm cutting, I'm creating a force parallel. That's a shear. Normal force is when I'm pushing down on this table or when I'm jumping up and down. That's a normal stress. And sort of the relative magnitude of the normal and shear stress depends essentially on the orientation plane. So if I'm pulling on a piece of plastic perpendicular to that surface, it looks like I have just a pure normal stress, force divided by the area. But if I instead draw this surface at an angle, I have a combination of shear, if I decompose that force into its components along this axis and that axis, it's going to have a shear and a normal. And it's a little bit arbitrary how I drew that square. The material doesn't know that I drew that square that way. These are sort of normal and shear stresses are going inside the material at all times. And we can actually calculate the range of normal and shear stresses by just looking at what is the orientation of the plane, and it comes out with these, I won't go into the trig, but basically it's functions of cosine and sine. So you can solve these. Now, when I'm bending a bone, what happens is on the top surface, I have tension stress. On the bottom, I have compressive stress. This is trying to elongate, this is compressing. And the magnitude depends on the distance from sort of the neutral axis, and that varies as the radius away. The way this works, though, it's still the force equilibrium that we talked about with Newton's laws. It turns out if I have the stress times a differential area, dA, so this is getting into a little bit of calculus, I generate a small incremental force, and then if I integrate over that whole surface, what do I have? I'm going to end up having a force, and I'm going to have a moment for that whole surface. So in the case of the internal resisting moment, that force, that differential force, is acting at a radius or a distance, which is called the neutral axis, or if you're in the shear, if you're doing torque on a cylinder, it's a radial distance. Let me just show you, this is where this comes useful. I want to figure out, if Grandma falls, is she going to break her hip? And what I need to do is, I have to figure out what are the stresses on the femoral neck where she's going to break her hip. So what we're going to do is that same free body diagram where we calculate the forces and moments acting on the femoral neck. So we have the reaction force at the hip joint, and we have body mass from going up in this direction. That's Fy. So we can take a reaction force, break it down into its components, Fy and Fx. And then if we now start looking at some of the forces in the x direction, this force has to be resisted by the internal stresses in the femoral neck. And my bending, sort of Fy, which forms this force couple, have to be resisted by these internal stresses, which is going to be tension on one side, compression on the other. If these internal stresses is more than the bone strength, the bone's going to break. And how do we figure out if the bone's going to break? So how many of you are familiar with Hooke's law? You had Hooke's law yet in physics yet? So F equals kx, it's the spring constant. Basically, Hooke's law can be used to determine the material properties of bone. It can be used to determine the material properties of everything. Instead of being a spring, the material now is the spring. So we literally do these tests. We take a piece of bone, we machine it, and we apply a force, and we look at how much it elongates. And this slope is the stiffness of the material. So for bone, this is pretty stiff. But if I actually have a muscle, it's going to stretch a lot. So the stiffness is going to be more like that. Now the problem is, I need to take the geometry or the shape of my specimen out of the equation to get at the intrinsic properties. So if I take my force and I divide it by the cross-sectional area, I get this internal stress. And if I divide by the change in length by the original length of the specimen, I get strain. So my Hooke's law now changes from force times a spring constant times a change in length to a stress times a stiffness, which is intrinsic to the material, times a strain, which is the displacement normalized by the original length of the material. And if I plot that out for different materials, initially you have that sort of spring constant, but then it starts to yield, it starts to break. And then eventually it'll just break in half. And for bone, bone has different properties in tension and compression. That is called anisotropy, and it has different material properties in different directions. So, piece of wood, you know, along the grain of the wood, it's a lot stronger. Across the grain, it's weaker. Your bones are exactly the same way. It's just like a piece of wood. There's an anisotropy, there's an orientation to it. And it turns out the bone is much weaker in shear and in tension in the transverse direction. Why is that important? Well, first of all, how many of you have heard of osteoporosis? This is what osteoporosis looks like. The trabecular bone, the spongiform bone at the ends of our joints, or what forms our vertebral bodies, starts to become more porous. So here's what you look like at 24 years old. This is what you look at 63 years old, and this is what you look at 89 years old. This is the cancellous bone compared to the cortical bone, which is what makes the shafts of our bones, that sort of hard, compact bone. So you can see the mechanical property differences are explained pretty much by porosity alone. So for cortical bone, if I do my force or my stress strain test, it's very, very stiff and it's very brittle. It breaks, doesn't take a lot of energy before it breaks. If I look at trabecular bone, for my healthy 24-year-old, sort of it looks like this. It's much less stiff than the cortical bone, but it can absorb a lot of energy because as I start applying force, those cells start to collapse down, and that absorbs energy. That's how the bumper of your car works. The bumpers of your car are these sort of rigid foams filled with oil so that it can absorb energy. And where's trabecular bone? It's at the end of our joint. So when I jump up and down, I want to absorb a lot of energy so it's not basically transmitted to my diaphysis where I can break my bone. Because I don't want to break my bone. If I'm skiing, I want to absorb the energy before my diaphysis, which is relatively brittle, absorbs it. And it turns out, just like we talked about at the beginning, bone fails at the weakest link. So remember, we said the bone will break when the force being applied exceeds the load capacity. So if I have a piece of bone that's non-completely uniform through its cross-section, the force is constant throughout here. But where do I have all my deformation? My deformation and my fracture is at the weakest link, where I have the least amount of bone, where the pores are the biggest. That's where I have my failure. And that's exactly what happens with our bones. When we're applying loads to the bone, it will fail at the plane where the stress in the bone, whatever its tension, compression, or shear, exceeds the capacity of the bone material. So remember, we said the bone doesn't really know how you drew your little square, but you can do methods where you can actually use calculus where you solve for what's the biggest and smallest amount of a stress, and you can solve for what plane, whether it's going to fail in tension, whether it's going to fail in compression. Now it turns out when I'm applying compression, I actually get an oblique failure, and I'll show you that that's because it's really failing along the shear plane. When we do bending, you get this sort of butterfly fragment, and with torsion, you get this sort of spiral-shaped fracture. That's because I get a butterfly fracture because it turns out that on the tension surface, the bone's going to fail in tension on the convex surface, but it turns out bone is really strong in compression, so this butterfly is at that shear plane. And that's where you get that butterfly. So basically, it's all, so when you're skiing or you're bending your bone or something, I can tell you how your bone broke. That's how people can actually do forensic analysis. Pathologists can look at a person and sort of figure out what happened to them by looking at the fracture patterns and figuring out sort of what were the loads that were applied that caused that. A spiral fracture, where I'm applying a twisting to the bone, it turns out that the plane that it actually fails in is on the tension plane, because the bone is weakest it turns out weakest in that tension plane, which is at about a 45-degree angle. And again, I'm not going to go too much into the math, but it allows you to calculate how a bone will break when you apply a certain force to it. The last thing that I want to kind of go over is a little bit about the structural properties, which is a combination of the material and the geometry. Geometry is important. So here I have a yardstick. If I bend this yardstick through its thickness, it's really easy to bend. If I flip that yardstick over and I bend it through its width, it's a lot harder to bend. I have exactly the same mass of material. I have the exact same amount of wood. The difference is how that wood is oriented relative to the bending forces that I'm applying. So a structure is more rigid when its mass is distributed away from that bending axis. And we call that moment of inertia. And it turns out that the moment of inertia varies. It describes the distribution of the material relative to the bending axis, and it varies as the fourth power of the distance. So that means for very, very small differences in the radius, it goes to the fourth power. I don't need a whole lot of extra material because it's to the fourth power. It's getting multiplied multiple times. Why is that important? Well, why do you think our bones are tubular? If I had a bone made out of solid that had an area of 2.77, it would have a certain weight. The moment of inertia is 0.61. Its bending strength we use as our reference is 100%. If I take that same area, but instead I make it a tube, So now it's hollow. So now I have the ability to actually have my blood system down the middle. That's where your bone marrow is. That's where your blood cells are made. I can now use that space because this isn't really supporting a whole lot of load. If you remember back from our where we had the stress, down in here, there's very, very little stress. It's mainly on the outside that's important. So for the same area of bone tissue, it's 50% stronger for the same amount of mass. If I make it a little bit bigger radius, it's almost 2 times greater. So the way we have tubular bones, because it allows us to have a lightweight structure, as opposed to if our bones were all solid, they'd be really, really heavy. We can now actually have it filled with marrow space where we can actually have another system, our hematopoietic system. And it turns out that the product of the area times the stiffness gives you the rigidity to a tension or compressive load. If we look at the stiffness versus moment of inertia, it's resistance to bending. And then the torsional rigidity is the shear modulus times polar moment of inertia, the resistance to torque. But why is that important? If we look at what happens as you get older and your bones start becoming osteoporotic, you see that between age 25 and age 85, that the strength and the stiffness of your bones keeps going down. Even the cortical bone, which was very, very robust, starts getting holes in it, starts looking like Swiss cheese. But what happens is our body compensates by geometry, but only in males, not in females. What happens is, in males, as the bone itself starts getting osteoporotic, the outside starts to expand. There's periosteal expansion. And that periosteal expansion helps compensate for the change in the material. The problem is women don't do that, which may explain why women have a much higher risk after they go through menopause of having fractures, having more likely risk of wrist fractures, hip fractures, spine fractures, because their geometry can't accommodate the same way that men do. So this is just showing how these, in male, with this periosteal expansion, it can help start compensating for what the material, as the material gets weaker, the geometry changes to compensate. Men can do it, and women, for either whether it's hormone related or lifestyle related, it's a little unclear. Women don't seem to have that ability to do it. It's probably estrogen related, with the diminution of estrogen that happens after you go through menopause. But the same idea of polar moment of inertia also explains how our fractures heal. So when I have a fracture, it goes through these stages of healing. How many of you have ever had a broken bone? Did you remember going to the doctor, you'd get an x-ray and they'd sort of, first, you got your x-ray, then 3 weeks later you got an x-ray and you'd get an x-ray to see how is the bone healing. And this is the callus that starts forming, and then that callus starts to remodel. And it turns out that what's happening is the material in that callus starts changing its properties, going from basically coagulated blood to sort of soft cartilaginous material to then calcified cartilaginous material to follow to basically this spongiform bone. What that is I'm starting to build a bridge. So I have this soft, kind of not very good material, but I'm putting a lot of it down real quickly. It's kind of like when you form a scab on your skin, it's a scab inside the bone. And I start building a bridge between the two bones, the two ends of the bone. But look what's happening. Remember we talked about moment of inertia? Here's what my normal bone should look like. What I do is I have this very, very weak material, but I'm putting a lot of it, and I'm putting it at a radius far out, so it goes r to the 4th. So even though it's crappy material, it's really weak, I'm putting a lot of it out, and I'm R to the fourth. So I'm able to kind of start stiffening that fracture and start stabilizing so the ends aren't moving. So how many of you, when you had your broken bone, noted somewhere around 3 weeks that all of a sudden you had less pain and you didn't feel that grinding motion? I mean, it's magical. It's around 3 weeks, everybody, it's like all of a sudden it doesn't hurt so much anymore. It's like I don't feel that grinding. Because what happens is initially this callus material, which is helping stabilize, starts to now dictate the new tissue that's forming inside the fracture gap. So what happens is, as this is expanding, I basically start making the rigidity or the movement of the material in this middle having a smaller strain. And it turns out from our biology that the strain in that gap controls the type of tissue that's formed. So if I have a whole lot of strain, 100% strain, I get sort of scar tissue, I get granulation tissue. It's kind of like the scar that you get when you cut yourself. But then, as I start sort of bridging, I now start, where my strains are only 10%, I start getting cartilaginous tissue. And now this whole thing starts getting even more rigid. I have less movement. Once my strains are under 2%, I actually start forming bone. And that's what you feel at 3 weeks. All of a sudden, you've now started to take your fracture, which had this sort of soft tissue, and sort of became bony. All right, I'm going to stop there. Enough physics class for the day, but any questions? Done? Okay. So, yep.
When I broke my arm, I got a metal plate put on it.
Mm-hmm.
Is that to help it so it doesn't move as much?
Exactly. So what happens is, by putting the metal plate on, we skipped all these steps. We pulled these two bone ends directly together and actually had direct contact. And we went, and so that brought our strains at the fracture to less than 2%, and you had direct bone heal. So the advantage of a plate is you skip all these steps, you can start movement earlier. The disadvantage is you had to have an operation. We had to basically make a cut in through your tissue, raise the muscle, expose the bone, put the plate on. And then the other thing is once your bone's healed, that plate's sort of extraneous. But a lot of people are sometimes bothered by the metal hardware, like they'll have some sort of soreness, so then you have the second operation having to take it out. So there's trade-offs. You have more efficient healing, you have better alignment, but it requires an operation.